Skew-symmetric matrices. So let's do an example looking at 2 by 2s. So if A is equal to A, B, C, D is, if this is skew-symmetric, then that means that A transpose is negative A, and this equation becomes A, B, C, D is equal to negative A, negative B, negative C, negative D. So what I get here is that A has to be negative A, C has to be negative B, B has to be negative C, and D has to be negative D. Well, if A is negative A, that can only happen if A is 0, and similarly D is 0, and the meaningful or more interesting equations are in the middle. So A has got to be zeros in the diagonal, and then you have a B and a minus B, like this. Okay, more generally, you're going to have zeros in the diagonal, and then this part above the diagonal is going to be the negative of what appears below the diagonal. So, some more examples would be, say in the 3 by 3 land, if I go 1, 3, negative 5, okay, the mirror image across the diagonal has to be the negative of the original. Oopsie daisy. So this is skew symmetric. Okay, fair enough. Let's try another example here. Now if I have a square matrix, A plus A transpose is automatically symmetric. Well, how do I do that? I'll say let x equals A plus A transpose, and I'll just calculate directly. X transpose will be A plus A transpose all transposed, and then I get, that's A transpose plus A transpose transpose, because the transpose does distribute across the plus. And we've seen the double transpose brings us back to where we started. And there we have it. We have proven that X transpose does indeed equal X. B. Exercise. Try this. Pause and try this. Okay. So I will say let X equal A minus A transpose. And then calculating X transpose, I'm hoping to get to negative X. So I do my transpose of X, I get A transpose minus A. And if I factor out a negative, I get what I want.